Hi, my dear student friends. Welcome to our channel, GATE Instrumentation Engineering Control Systems. So today we are going to discuss about the steady state error. Okay, steady state error in the control system. So first we see what is steady state error. See here, the error is nothing but expected output minus actual output. So E of t equal to expected E of t is error, R of t is the expected output. Suppose this is in suppose it's a unity system, unity input, then R of t. It is with the gain of k, then it becomes gain of the system, right? So the from this unity feedback control system, the D of S is the reference input. D of S is the controller. R of S is the reference input. U of S is the actuating signal or manipulating variable Okay, so the error difference from this diagram is E of S equal to R of S minus C of S, where the U of S equal to E of S into D of S. The U of S actuating signal, E of S into this. Let us consider this case where the R of S equal to step input, that is 1 by S. The plant has no poles at the origin, that is it has a finite DC gain. So the controller is a very simple gain fit block. Okay, controller is a simple gain block. So understand. So let us have the unity feedback with the forward path gain is a simple DC K, right? So C of S. So in steady state, input equal to output equal to input. Steady state error is 0. So when E of S equal to CSS equal to RSS. So when steady state error is 0, CSS equal to RSS. Okay. So steady state error from this substitution, the C of S here is nothing but ESS, right? ESS into K. So if you put like this, steady state error equal to RSS, reference steady state into 1 by 1 plus K. The non-zero steady state error is a step input for a finite steady state forward path gain. Okay, so that means is if the RSS equal to 0, then ESS is not equal to 0. So it implies the finite DC gain. The finite DC gain implies no poles at the origin. No poles at the origin. Understand? No poles at the origin. Clear? So now let us allow a simple pole. Okay, simple pole at the origin. That is integrator in the forward path. Let us have a single pole at the origin. So K by S is the pole at the origin. So R of S equal to E of S into K by S. So from this, the error from the block diagram, unity gain block diagram, E of S equal to R of S minus E of SS K by S. Right? So if you simplify this by replacing R of S equal to 1 by S, you will be getting E of S equal to 1 by S plus K. Okay. So what is here? So from this is the final value theorem. We obey the final value theorem here. We obey the final value theorem. Understand? So what is the final value theorem? E of t equal to t tends to infinity, limit s tends to 0, s into E of S. So if you apply here, you will be getting s by s plus k. If you substitute s tends to 0 steady state error to a step input when there is a integrator, right? And there is a integrator in the forward path. Clear? So consider a ramp input to the same system, same integrated system. What happened? The R of t equal to t for the ramp input. In general, it is k by t, kt. So R of s equal to 1 by s square, or k, if we ask k by s square. So now the error is E of s equal to 1 by s square into s plus k. If you simplify this, the steady state error ESS equal to limit s into E of s, limit s tends to 0. If we put this, we will be getting 1 by k. Okay, that is k. So now non-zero but finite steady state error to ramp input when there is an integrator in the forward path. We will be getting this, right? So from the above discussions, we observed that the steady state error is related to the number of integrator in the G of S, and the steady state error is related to the type of the system, type of the input. Okay, this is type of the system, this is type of the input. So your steady state error equal to this. What do we get? This is the formula for steady state error. So the steady state error is the function of R of S, type of input under the system. Okay, the type of the input is nothing but step ramp parabolic. The type of the system is nothing but number of integrators present in the system. Based on the number of integrators present in the system, we can classify system as type 0, type 1, type 2, type 3, etc. Okay, so this is number of integrators in the system. Okay, then the system type, the degree of the input polynomial for which the steady state error is a finite. So finite and non-zero, right? Finite and non-zero. The type 0 system will give finite output and non-zero error to a step input. So type 1 system will give finite non-zero error to a ramp input. So type 2 system will give finite non-zero error to a parabolic input. So based on the system, so we can classify, for example, the type 0 system, G of s equal to s plus 4 divided by s plus 5, s square plus 8s plus 7. So in this system, you observe the s integrator present the denominator. So only s power 0, 1. So s power 0, 1. So type 0 system. G of s equal to s plus 3, s into s plus 1, s plus 5. Here s has 1 power, 1 degree. So this is a type 1 system. So similarly, you see in this system, the s to the power, there are 2 integrators in the denominator. So this is called a type 2 system. In general, G of s equal to k, it is similar to this. You see the denominator s power n. S power n. N is nothing but the number of integrators in the denominator. If n is 0, type 0 system. If n is 1, type 1 system. N equal to type 2 system. Understand? So let us first apply step input to the system. Okay, step input. Step is nothing but the position input. So for step input, R of s equal to 1 by s. So you just we apply in the standard expression. ESS equal to limit s by s0, s into A of s. Substitute instead of R of s, k by s, we will be getting finally a limit s tends to 0, 1 by 1 plus g of s. So if you apply the limit to the g of s, actually we don't know the actual type of system g of s. G of s may be type 0 system, type 2, type 3, etc. So we simply replace the limit s tends to 0 g of s as kp. So we can call it as kp equal to static position error constant, right? So static position error constant. What is kp? Kp is nothing but kp equal to limit s tends to 0 g of s. This is about the static position error constant. Let us apply ramp velocity input here. So for ramp input, R of s is k by s square in Laplace term domain. So ESS equal to limit s tends to 0, s into R of s divided by 1 plus g of s. limit s tends to 0, k by s into 1 plus g of s. Substitute here, we will be getting s square plus s plus s into g of s. So if you substitute s equals 0 here, ESS become k divided by limit s tends to 0, s into g of s. Again, we do not know the nature of the system type g of s. So this can be replaced by kv, that is static velocity error constant. So kv is nothing but limit s tends to 0, s into g of s. Understand or not? Okay. Then next let us apply parabolic or acceleration input to the system. So the parabolic input, the Laplace transform of the parabolic input is nothing but r of s equal to k by s cube, right? So e of s equal to limit s tends to 0, s into r of s divided by 1 plus g of s. Instead of r of s, k by s cube we apply here. Okay, so k by s cube. So s is cancelled. We will be getting k by s square plus s square g of s. So ES is equal to k divided by limit s tends to 0, s square g of s. If we can replace this limit s tends to 0, s square g of s, right? So k equal to static acceleration error constant. So k equal to limit nothing but k limit s tends to 0, s square g of s. So these are all the various the response of the error steady state error response for various types of input. From the input we derive the position error, static position error constant, then static velocity error constant, and static acceleration error constant. Okay, let us analyze the various type of the error response for various type of input. Okay, sorry, various types of system. Okay, that we will continue, right? The error response for various type of system. Okay, so what happened the various type of system? So first we know the previous section. You see for step input, the steady state error become a constant, right? As you see, for the type of system, type 0, finite non-zero error to step input, whereas for state type input, type 1 system. Okay, so what is the type 1 system? So the type 1 system for step input, for the type 1 system for step input, the steady state error is 0. Okay, type 1 system steady state error is 0. Similarly, for the type 2 system, see, type 0 system has finite steady state error. Okay, has finite steady state error. Okay, so finite steady state error. Whereas for steady state error for step input, Similarly, for type 1 system, okay, type 1 system for step input. Okay, type 1 system for step input is 0. Similarly, type 2 system for the step input, 0 steady state error for step. Type 2 system for step input is also 0. Okay, so 0 for step input. Then type 3, say type 3 system, also 0 steady state error for step input, right? So this is all the analysis for step input for various type of system. So the step input, for the step input, type 0 has finite non-zero steady state error. Okay, finite non-zero steady state. Whereas type 1 system has zero steady state error for step input. Type 2 system also has zero steady state error for step input. Type 3 system has zero input for steady state error. Similarly, for ramp input, okay, ramp input, and this response for various type of system and various type of system types, okay, type of G of S, whether type 0, type 1, type 2, etc. Clear? So what are the response? So type 0 system gives, okay, infinite, okay, infinite steady state error for ramp input. So type 1 system has finite, okay, finite steady state error for ramp input, Similarly, type 2 system has zero steady state error. Then type 3, consider type 3 also gives zero steady state error for ramp input. Similarly, for parabolic input and for the, what is the response for various type of system, okay, parabolic input and various types of GFS, type G of S. Okay, so what is the various type? So what is the response for type 0? Type 0 system for parabolic input, Type 0 system for parabolic input gives infinite, okay, infinite steady state error. So the steady state error is infinite, okay. Then type 1 system also gives infinite steady state error. Then type 2 system gives finite non-zero steady state error. Type 3 system type 3 gives zero steady state error. Okay, so we know the various constants. Okay, what are the various constants? So static error constants, right? So for step, we see it to be input for when we consider input, static error constants. Okay, static conclusion, static error constants. Okay, static error constants. So for each input, we know for each input what is the steady state error. For step input, the steady state error equal to 1 by limit, okay, 1 plus limit s tends to 0 G of S, okay, G of S. For ramp, the steady state error equal to 1 by limit s tends to 0 S into G of S. Okay, for parabola ESS equal to 1 by limit s tends to 0 S square G of S. Okay, so this can be written as the limit term, each expression For static error constant associated with the particular input. What associated with the particular input? For what are the particular input? The constants. Okay, you can remember like this: position constant, position constant. What is position constant? Kp equal to limit s tends to 0 g of s. Okay, then velocity constant, velocity error constant, velocity constant. Okay, what is kv? Okay, kv equal to limit s tends to 0 s into g of s. Then acceleration constant, ka equal to limit s tends to 0 s square g of s, s square g of s. So these are all static error constants and their error. So this is kp, this is kv, this is ke, right? So we can sum up in a tabular column. Okay, so we can remember this in a matrix format. We can remember this in a matrix format. Let us see. Say this is type. We can have this is type. This is steady state error. Okay, steady state error, ESS, right? So step, we are giving step, okay, step as a k by s. Ramp input, these are all inputs. So you can have this type. So you can have this as a, you can type and input. So ramp, okay, what is ramp? For ramp, k by s square. Then parabolic. What is parabolic? K by s cube. K by s cube, right? So for type 0 system, 1, 2, 3. Sorry, 1, 2, 3. Okay, type 0 system, type 1 system, type 2 system, type 3. We go up to type 3 system, right? So for type 0 system, for step input, it is finite. So that finite value is k by 1 plus kp. Whereas type 0 system for ramp input is infinity. For type 0 system, parabolic input is also infinity. Similarly, type 1 system, step input is 0. Type 1 system, ramp input is finite, that is k by kv, right? Then parabolic input, type 1 system is infinity. Then type 2 system, step input is 0. Type 2 system, ramp input is also 0. Type 2 system, parabolic input is finite. So the finite value is k by ka, acceleration constant. Then type 3 system, step input is 0. So type 3 system, ramp input is 0. So type 3 system, parabolic input is also 0. So this is the matrix format for remembering your steady state error and its corresponding constant for various inputs. So important note that the if this is very important, if the type of system, increases from 0 or 1, 2, 3, like etc. increases, the type of the system increases, the error, steady state error decreases, okay, and accuracy all increases, but main important thing is stability decreases. Type of the system from 0, 1, 2, 3, etc. increases, the error decreases, then accuracy and the accuracy also increases, but stability decreases. So with this, the various static error coefficients have been discussed. Next, we see some example to calculate the estimate the steady state error. Okay. First, see the example number 1. See, let us see some examples. The worked out examples, the gate questions to solve based on the static error coefficients. Static error coefficients. So first, this example number 1. This example, this question is very important. 1. See, a thermometer possessing a thermal time constant 5 minutes, 0.5 minutes is introduced in a bar where the temperature is increasing at a constant rate of 5 degrees Celsius per minute. The steady state of the thermometer is, okay, so what is A, 10 degrees Celsius, B, 2.5 degrees Celsius, C, 0.1 degrees Celsius, D, 0.4 degrees Celsius. So how to estimate the steady state error of the system? So the actually the feedback system, you can consider the feedback system. The thermometer is given. Consider the block diagram, unity feedback control system. The thermometer of first order, okay, first order system whose tau s time constant. This is in a closed loop feedback. So R of S. So the forward path transfer function is 1 by tau s. This C of S. This is our G of S, thermometer. So this is E of S, error. So let us find the steady state error for the system. So the closed loop feedback of the system is C of S by R of S. C of S by R of S equal to solution. Solution C of S by R of S equal to, this becomes 1 by 1 plus tau s, where tau equal to, tau is given, time in the time constant, the rate is given, time constant tau equal to 0.5 minute, tau equal to 0.5 minute. So first to convert, we observe the unit. If it is given in minute, we follow same in terms of minute. If it is in seconds, you convert both, you maintain both rate as well as that also in a same unit. Clear? So the input is okay. So the type of input. So type of input is a ramp. You see the rate of this is increasing at a rate. Increasing at a rate means input is ramp. Okay, ramp. So with the rate of 0.5 means it is not unity ramp. It is R of t equal to k times t. K times t u of t. So the rate k is given 0.5 degrees Celsius per minute. Okay, that's sorry, 5 degrees per minute. So R of t equal to k times t, 5 times t into u of t, 5 times t. So k is given 5 degrees Celsius per minute. So given tau equal to 0.5 minute, input is R of t equal to 5 times t u of t, 5 times t u of t, right? So what is so we have to find the steady state error. Okay, first to find out velocity error constant. Velocity error constant. Understand or not? So the open loop transfer function is open loop transfer function g of s equal to 1 by tau s. 1 by tau s. So what is error? So error is nothing but K by KV. K by KV. What is K? K is the system gain. So the input with the weightage of K. So K is 5. 5 divided by KV. Right? So also you know that what is this is equal to KV equal to, so K equal to 5. KV is 1 by tau S. So S for S equal to this. So what is KV? So KV velocity error constant equal to limit S tends to 0 S into G of S. Okay. So limit S to 0 S into G of S is 1 by tau S. So SS cancel only tau. So KV equal to 1 by tau. So KV equal to 1 by tau. See, KV equal to 1 by tau. So what we are getting? So a steady state error equal to K by KV. So KV equal to 1 by tau. 1 by tau. What is tau? Tau is 0.5 minute. 1 by 0.5 minute. So 5 divided by 0.5 minute. 5 degrees Celsius per minute divided by 0.5 minute. Clear? So what do we get? We are getting only minute cancel. 5 degrees rate is 5 degree per minute, 0.5 minute. KV is 1 by 0.5. Sorry, 1 by 0.5. KV is 1 by 0.5. So minute cancel. We will be getting 2.5 degree Celsius. So this is the answer. What is the correct answer? 2.5. So B is the correct answer. So answer is B. Okay, next question. The open loop transfer function of the system for a unity feedback system is given below. Which system will have more steady state error for unit step input? Whether A or B or C or D, which has more steady state error? Okay, whether option A, option B, option C, option D. Right? Let us find. Let us do analyze solution. Okay, solution. So which system has more steady state error? First, let us check with the first system. Okay, for unit step. Okay, for unit step, what is ESS for unit step? For unit step, ESS equal to 1 by 1 plus limit S tends to 0, G of S. Okay, S tends to 0, G of S. Right. First, we put limit for, you see, limit S tends to 0 for the all the denominators. Okay. So what do we get? So 0, 0, 0. Okay. What is remaining? 1, 2, 3. 2 into 3, 6. 80 by 6. Right. So 80 by 6. 80 by 6 is the KP value here. Okay. For this, KP equal to 80 by 6. For this, KP equal to 120 by 15. 120 by 15. So putting this, apply this rule to this. 120 by 15. Next, for this, S0, 0, 0, limit 0. For everywhere. So 0.5 into 3, 1.5, 1.5 into 5.5. KP in this case equal to 60 by 1.5 into 5.5. Am I right? So this becomes 40 times. Divide 40 times 40 by 5.5. 40 times. Understand? 40 times. Here, similarly, here S0, 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 4 into 15, 60, 120 by 60. 120 by 60. So which has more steady state error? C 12 by 6. So Kp value for this case 12 by 6 is 2. So 2. Here Kp value is 40 by 5.5. Say approximately you see 5 times more than 8, almost 7. It comes around 7. So this comes 7. Okay. So here in this case 3 times 5, 2 times 24 times 24 by 3, 8. So in this case 8. In this case say almost 6. What do you get? 2, 20, 3 times. So the Kp value is lesser in this case. If Kp value lesser in this case, you see what is steady state error? 1 by 1 plus Kp. 1 by 1 plus Kp. If Kp decreases, steady state error increases. Okay, so Kp value which is smaller, the 2. Okay, so in fourth case in the second problem, 4 answer is D. So D has more steady state error. So D answer is option D. Clearer. This is the simplest way of estimating the steady state values. Okay, steady state values. So in this case, steady state value. So if you substitute here, we will be getting in this first case for the case 1. See, I will tell also. Option A, steady state error equal to almost 1 by 1 plus 80 by 6 is how much? 13. 13 something. Okay, around 13. 1 plus 13 point something. So we will be getting 0.069. In the case B, steady state error equal to 1 by 1 plus 8. Okay, 9. 1 by 9. 1 by 9 is almost 0.11. So in the case C, steady state error equal to 1 by 1 plus 7 point something. Okay, 7 point something, 7.27, almost 7.3. So we'll be getting 0.12. The case of D, steady state error equal to 1 by 1 plus 2. Okay, 1 by 1 plus 2. So 3. So 0.33. So which this has more steady state error. That's the correct answer. Am I right? So the next problem is, which one of the following is the steady state error of a unity feedback system with the transfer function 10 by s square plus 10s plus 10 applied to a unit ramp input? Which one of the following state it has steady state error for unity feedback system? Following is a, so for this transfer function, which is the steady state error for unit ramp. See, just observe this transfer function. This transfer function is in a closed loop format. It's not in a open loop format. Whereas for calculating the steady state error, we use only open loop transfer function G of S. Okay, G of S. So, but this is the transfer function, closed loop transfer function. Okay, so closed loop transfer function T of S equal to open loop transfer function G divided by 1 plus G of S, 1 plus G. So from this, what is G of S? So G of S equal to T of S divided by 1 minus T of S, right? So this is the relation between open loop to closed loop to open loop form. Okay, so solution using this solution, which one is the first? Let us find the open loop transfer function G of S from the closed loop transfer function. Clear or not? So G of S equal to T of S, 10 divided by S square plus 10S plus 10 divided by 1 minus 10 divided by S square plus 10S plus 10. So you simplify this. So take LCM in the denominator, numerator, denominator, and denominator cancel. So we'll be getting 10 divided by, you bring this to here. So S square plus 10S plus 10 minus 10, 10 cancel. So we will be getting G of S equal to 10 divided by, take S as a common term, S into S plus 10. So what you observe from this G of S is a type 1 system. So type 1 system has, for a ramp input, type 1 system has a finite error, finite constant, finite steady state error. So not zero. You see, go back here. See here, for a ramp input, type 1 system will give this value. Okay, ramp input, type 1 system will give finite value. Other than, see, for other than this is zero. So infinity is impossible for the system. So zero also impossible for the system. Okay. So infinity also impossible, zero also impossible. So option A and option C. Okay, option A and option A is and option D are not fit for the solution. Since the open loop transfer function is 1. If the open loop transfer function is 1, then it gives a finite input, finite error, steady state error, finite steady state. Understood or not? Finite. So there is a choice only between B and C. Okay. Let us apply the error, steady state error for ramp input. Steady state error for ramp input is 1 by KB. So what is KB? Where KB is limit S tends to 0. Okay. S into G of S. S into G of S. So limit S tends to G of S. S into G of S equal to limit S tends to 0. S into, what is G of S? 10 divided by S into S plus 10. So SS cancel. If you apply S equal to 0, so it becomes 0, 10, 10 equal to 1. So steady state error equal to 1 by 1 equal to 1. So which answer is correct? Answer C is correct. Answer C is correct. So C is the correct answer. So C is the correct answer. Right? Good. Then the Laplace transform of f of t is f of s. Okay, the Laplace transform of f of t is f of s. So given f of s equal to, so given, what is given? Given solution. So f of s equal to omega by s square plus omega square. What will be the final value of f of t? So what is the final value of f of t? We have to find the steady state value. Final value or steady state value is one and the same. Okay, steady state value and the final value. So what is the final value? So the first find the poles of the f of s. So the poles of f of s are at s equal to plus or minus j omega. So where in the s plane, the plus j omega and minus j omega. So the poles lie on the imaginary axis. So system or function oscillates. This is a marginally stable. Oscillates with a fixed amplitude. And of frequency omega radian per second. So the system oscillates with with a fixed amplitude of frequency omega radian per second. Hence the steady state value, not error, steady state value can't be determined. Okay, can be determined. So which is the answer? D is the answer. None of the first infinity or 0 or not 1. So none of these the correct answer. Correct answer is D. Okay. Next, the unit impulse response of a second order underdamped system starting from the rest, that is C of t is given. It is starting from the rest. So 12.5 e to the power minus 60 sine 80, where t is greater than or equal to 0. The steady state value of the unit step response of the system equal to, we have to find the steady state value of the system. So answer is A equal to 0, choice B is 0.25, choice C is 0.5. So let us find what is the solution for this system. So what is given? C of t is given. So C of t is given. Solution. C of t is given. What is C of t? 12.5 e to the power minus 60 sine 80, where t is greater than or equal to 0. Okay. So first let us find the to find the steady state value, we have to use the final value theorem. So for final value theorem, for the case of simplicity, first convert it to S domain, then only we can easily. So what final value theorem says? To find the steady state value, limit t tends to infinity, E of t or C of t, final value C of t equal to limit S tends to 0, S into C of t, S into C of S. This is based on final value theorem to find the final state or steady state output of the system. So from the given, let us find, first step is determine C of S. Okay, C of S. How to determine C of S? Applying Laplace transfer function. So C of S by R of S. So C of S by R of S equal to L inverse of, Laplace transform of C of t. So what do you get? 12.5. So what is the Laplace transform? E to the power means, so e to the power minus 6 means, so we can apply here one more property we can apply. What is that? E to the power minus at sine bt. Okay, sine bt. If it is like this, we can write this expression. This is Laplace transform of e power minus at sine bt. This becomes b by s plus a the whole square plus b square. So same thing can be applied here. So 12.5 shifting theorem. Okay, 12.5 into 8 divided by s plus 6 e to the power minus 6 whole square plus 8 square. So this is our C of S by R of S. So what is C of S by R of S? The closed loop transfer function. So C of S you know. So step input. R of S is the step input. So okay. So what is C of S? For the unit step, just S into this into 1 by S, right? So C of S, from this C of S equal to 12.5 into 8 divided by S plus 6 whole square plus 8 square into R of S. What is R of S? 1 by S. So now find the steady state output. So the steady state output value for step input equal to limit S tends to 0, S into C of S. Okay, so limit S tends to 0, S into, what is C of S here? C of S 12.5 into 8 divided by S plus 6 the whole square plus 8 square. S plus 6 the whole square plus 8 square into 1 by S. This is R of S. S cancel, remaining thing. Now put S equal to 0 in this expression. We will be getting the steady state output. Okay, steady state value equal to 12.5 into 8 divided by 6 square, 36 into 8 square, 64. Okay, 8 square, 64. So, or keep it as 8 square. So square 8 cancel. Okay, so 12.5 into 12.5 divided by S square, 36. 36 into 8. 12.5 into 8. S equal to 0. So S equal to 0, 6 square, 36 plus 8 square, plus okay, 8. So 36, 6 square plus 8 square, 8 square, so 64. So this becomes 64, this is 8, sorry for this inconvenience. See, so the steady state value becomes 12.5 into 8 divided by 6 square. By putting S equal to 0 here, 6 square plus 8 square. So 6 square plus 8 square is 10 into 8, 100. So 100 equal to 1. The correct answer is 1. 1 is option D. So 1 is option D. This is the correct answer. Understand? So D is the correct answer. So answer is D. Answer is D. Right? Answer is option D.